I'm going to start in perhaps with a little bit of review of a couple concepts that I've had, and we're going to go through the rest of limits that don't involve infinity, and we're going to get into the definition of continuity. Okay, so this rule is that if f at x equals g at x when x doesn't equal a, then this actually is incomplete. I got to change it. Oh yeah, this works. Okay, I'm sorry. This is complete. I was misreading my own notes here. If the two functions are the same everywhere except perhaps one value, that the limits as you go to that value are the same. Okay, and where this applies is if we have something like this, where we want to find what is the limit as x approaches 1 of this thing. So we don't have a value for f at 1 because 1 is not in the domain. You get the indeterminate, 0 over 0. But if we look at this and recognize that if we cancel out the x minus 1s, we get 1 over x plus 1, and I'm going to define that as g at x. So everywhere except at 1, these two functions are identical, right? Anything you put in here will be in here. So you might think of this as kind of simplifying the function, and in fact it is, but if you truly simplified it, you'd have the domain restriction that x does not equal -1, or x does not equal 1. We'll ignore that for now. We'll just make use of this for the fact that we're not really interested in what happens when we're actually at that value. It's what happens as we approach it. And you can imagine that as you get closer and closer to 1, this is going to get closer and closer to it gets closer and closer to 1/2, right? Because as this thing, from the bottom, if it's just a little bit less than 1, it gets closer and closer and closer. The denominator will get closer to 2. Same thing coming from the top. As you're at something like 1.00001, the sum will be 2.00001, and you'll get this thing that's close to 1/2. And so we can take something like this and simplify it and make use of that rule so we can more easily calculate limits. Because this one we can get by inspection. This one, probably most of us couldn't do that in our head pretty readily, right? I mean, you can plug in a 1 and you get 0 over 0. So, but here, if we plug in a 1, we get 1 over 2. Yes?
So the a value that you're referring to is always going to be where like the limit is? That
yeah. Because all other values are the same. I'm looking for where it goes to the limit. Okay. And so it's almost irrelevant if it doesn't equal the value that we're trying to get to in our limit. It's one outside. Yeah. So if we think about how you graph this, that 1 over x, x plus 1, this is going to be moved over to an asymptote here of -1, and it's going to look like 1 over x. And so the question here is, what happens as x approaches 1? Now my original function has that hole in there, and so what I've done is I've essentially removed the hole. I've said, okay, these functions are identical. This thing would be the x minus 1 over x squared minus 1. Without the hole, it's this one, so I'm going to evaluate this one because that's easy. Okay, so let's look at this now. We have f at x equals x squared, and we want we want to find the limit of this difference quotient as h goes to 0. And so what I'm going to do is expand it. And then simplify it. Now, this and this aren't the same function, right? Because this one, h, when h approaches 0, or when h is 0, we get 0 over 0 here. But when h approaches 0 here, we get 4. All right, so the two functions are the same except when h equals 0. But since we have one where they're equal, the limits of both of these are the same, and so we get this limit as h approaches 0 is just going to be 4. And this is going to be the method, the primary mechanism that we're going to use to calculate derivatives using the limit definition of derivatives. Okay? Oh, you already have this in your notes, right? I showed you this on Monday. But that's okay. I know I go too fast when I start showing a lot of these equations.
Wait, so you just ignore the h?
You don't ignore it.
What is
I'm finding the
h
limit
equals
as
zero?
h goes to 0 of this. The closer I get to 0, the closer this gets
So
to
4
4.
plus 0 equals-
So we say that, yeah, the limit is 4. Here, if I put in a 0, here I have 2 squared minus 2 squared, which is 0, 0 over 0. Here, it definitely is part of the domain of 4 plus h when h equals 0, but here we have to exclude the domain. Okay, so there's going to be a bit of algebra that will be challenging, and I'm going to show you one trick that you should always keep in mind when you see square roots. Okay? Can I go on now? This one involves square roots. This doesn't simplify in any, nice algebraic fashion if we just try and, I don't know what you would even try. The way to get rid of a square root like this is by multiplying the expression by its conjugate. Okay, so the conjugate of this is we take, notice we have two terms with a difference. We take the same two terms with a sum. And so we have these two. And what we're going to get is that that radical expression is going to be squared, so we just get 1 plus h, and we have this 1 that's also squared, that gives you 1. And so we have now no longer a radical in the numerator, but 1 in the denominator. But the 1 in the denominator isn't going to hurt us because it's the sum, not the difference. And so if I simplify this, 1 plus h minus 1 is going to be h, and so I have h over h. And then this becomes 1 over the square root of 1 plus h plus 1. And look what happens. As h goes to 0, this expression, the square root of 1 plus h, is going to go to 1, right? Because this will, inside the square root is going to be 1. Take the square root of 1 and we have 1, so we have 1 plus 1 is 2. So we don't get the indeterminate form. Here we got a simplified version that gives us something that's very definitely within the domain of this expression has h equals 0 as part of the domain, so we can make a substitution and arrive at a numerical value.
So then the limit as h approaches 0 would be
1 half, right. And if you just plugged in the 0 here, you'd get 0 over 0. So it's just one of those tricks to keep in the back of your mind, that when you have to evaluate the difference quotient with radicals in the numerator, you want to use the conjugate. Yes?
Okay, I got up until you got 1/2, and I don't understand.
You don't get how I got 1 half here? Okay, you see as h approaches 0, 1 plus h is going to go to 1.
So you plug in the 0 once you get to
Yeah,
Oh,
yeah. Okay, so remember I mentioned this, that the limit only exists if you get to the same limit coming from both the positive side and the negative side. Okay? And that's part of the definition of a limit existing, is that you have to come from both the positive and the negative side. And I think I showed you this with the absolute value, that when you have the absolute value and x is approaching from the negative side, the function actually equals negative x, right? So the absolute value of -1 is -1, which is 1. that's less than 0. Greater than 0, it doesn't do anything. So these both evaluate to 0. So even though we have a piecewise function, it goes to the same place. And so in order to find this limit, we want to evaluate it from the positive and the negative side. And sure enough, we get the absolute value of x. The limit as x approaches 0 is going to be 0. And you can see this on your on a graph. The graph of the absolute value of x looks like that. I come from this direction, I'm heading to 0. Come from this direction, as I get closer to 0, y is going to be 0. Okay? Now you have a few exercises in your book, and in fact your book has a whole section on one-sided limits. And I think if you understand this and understand the fact that when you have, let's say, a piecewise function that looks like this, if let's say this is a 2, the limit of this function as x approaches 2 does not exist because it's a different value when it comes from either direction. Okay, and that's really the gist of the one-sided limit section. That's 1.4 in the book. I'm not sure if I want to talk about this in a lot of detail, but I'm going to, just for completion, go through this. So if this escapes you, what I'm talking about, don't worry about it, but I hope you can pick up a little bit based on what I've just talked about. When you see this kind of open bracket like this with the open spine on it, what that means is it's the largest integer that's less than or equal to x. And so the largest integer less than or equal to 4.8 is 4. When it is 4, it is 4. When it's negative 3. But here's the tricky part now. The largest integer that's less than or equal to negative 32 is actually negative 4, right? Because negative 3 is actually larger than negative 3.2. So this is a function. It's not the absolute value, but it's kind of a tricky function in the sense that it does different things depending on whether you're positive or negative. So if I were to make a graph, this is what it looks like. So if I'm at here 4.8, it equals 4. When I'm at 4, it equals 4. When I'm at negative 3, it equals negative 3. But if I'm at negative 3.2, which is over here, I'm actually on this one here, which is going to be negative 4. Okay, so the limit as x approaches 2. From the negative side, the limit is 1, right? Because as I get closer and closer to 2, but not quite arriving at 2, I'm always going to be 1. When I come from the positive side, when I'm at 2 and a fraction, going down to 2, I'm going to be at 2. And so here's a case where this limit doesn't exist because I'm coming to two different values when I'm approaching x equals 2. Okay, and that's really the only point I want to make with this. Don't worry about the function so much other than the fact that it graphs out like this, and you can see that I have, when x is approaching from this way and x is approaching this way, where x is approaching 2, I get two different values. So the limit at each of those steps, if you want to look at them that way, does not exist. Although within them, you know, the limit definitely exists when x is approaching 2.5. But when it approaches an integer, it doesn't exist. Okay, so here's another theorem. So if my function is always less than another function, when x is near a, except possibly a, and those two limits exist, that the limits have to have the same relationship, where the limit of f is going to be less than the limit of g as x approaches a. Now this might seem kind of obvious, right? If I'm always less than something else, whatever I approach, I'm always going to be less than that other thing. But it's actually a theorem that needs to be proved, but it's one that, you know, is going to be be used when we develop a few more concepts in derivatives. And then here's something called the squeeze theorem. And this was actually, you probably read this in your section. This is in 1.3. And I'm not going to talk a lot about it just because this usually comes into play when you have trigonometric functions. But what this says is that if I have a function that's always in between two functions, and that those outside functions approach a number, then that that function that's between them will approach the same number. So let me just draw a diagram of this to kind of show you what I'm talking about. Let's say I have h at x. No, h at x is the biggest one. Let's say this is f at x. Okay? And I have h at x here. Now, I have a g at x, and let's say it goes crazy, but it's always in between those two. If the limit, as I approach a certain value, is going, or if I go to infinity, you know, like with my asymptote, if this is always going to be below this, and this is always going to be above it, and these two limits are the same, let's say they approach the same asymptote, that function that's in the middle will also approach the same asymptote. And so where you're going to use this is when you start to talk about trigonometric functions and you have really complicated functions, but you can simplify those functions by making some, by removing some trigonometric functions. So just keep this in the back of your mind, the squeeze theorem. It logically fits into this part of our discussion on limits, but it's basically not going to be a big factor right now. Yes?
At the top where you say limit of x is less than limit of g of x, like what would that look like if the limit is less than that?
Oh, that's just like this. Okay? This is always less than or equal to the limit of h at x, because f at x is always less than h at x. Yeah. Yeah, let's see. I didn't get to continuity.